So welcome back. So today we continue with the Kalman filter. And remember, guys, we said that in fact the Kalman filter applies to dynamic least squares. In fact. So the word dynamic means that even without new data, the state vector is changing with time. Could be changing. So for example, if X gives the position of a GPS satellite, then the position will move about delta X with respect to the time, which is equal to V delta T, V is velocity. So this approximation, or a better one, will be the state equation for X n plus 1 at new time. And a new measurement comes, which could be called B n plus 1, at some instant of time, which is T plus delta T. And this would be used to further update the approximate position, which is X hat new. So in the matrix form, we are adding two new equations, the state equation and the measurement equation. So you can say that in state form, this is the new A you get, okay? And this comes as the new state equation, and this is the new measurement equation, as we said, okay? So in general, what do we want? We want the least squares solution of this equation. So what makes the Kalman filter, in fact, the most, truly the most impressive, or one of the most impressive tools in data science, is that the state equation itself and the measurement equation have their own covariance matrices. In fact, we call these reliabilities. So these equations, or those equations, are in fact inexact. So there is some tolerance or some error in measurement or in the state. Okay? So, but the variance or covariance measures have their different reliabilities. So this is what we are saying. So the normal equation, which we've seen before in the case of the least squares, should be weighted using the V minus 1, the inverse of the variance matrix. And the system becomes ATV minus 1, X hat equals ATV minus 1. So in reality, V itself has to be updated at each step. So Kalman, in fact, updates the XO, or the estimation, in two steps. First of all, he updates the projection, and then comes that comes from the state equation, and then comes the correction, which is the X hat new, using the new measurement based on zero correction objective. Okay. So let's see the updating scheme. So mainly the updating scheme used is that X hat new would be equal to X state plus K, which is in general in the matrix form called the Kalman gain matrix, times V minus Vn plus 1, which is the measurement or the new measurement, minus R, which is the kind of reliability coefficient, times the X hat state, or the old estimate, if you wish. So the gain matrix K is created from A and R, and in fact the covariance matrices V state and VB. Okay? This is in matrix form. Just right now, we'll see a small example which could explain much better what we are talking about. So if the new Bn plus 1 agrees perfectly with the prediction X hat state, then in fact there is a zero correction, because in fact what happens here, you get a 0. Okay? There is a zero correction from X state to X. And we also in general need to update the covariance of the whole system, measuring the reliability of the new measurement, or of the new estimation, if you wish. So in fact, this V is often the most important output. The most important output we can carry with you is the way you update the covariance of the whole system, measuring the reliability, in fact, of your estimation. It measures the accuracy of the whole system of sensors that produce your final estimate. Okay, so let's see with a small example. For the first example, this is a one-dimensional problem, guys. So just to simplify, to get things, at least understood on unidimension. So what are we trying to do here? In this example, we are trying to do what? To estimate the true temperature, the exact temperature, okay? Based on a number of previous measurements, estimations, and estimation errors. okay, and estimation errors. So let's, for example, here, suppose that there is a new measurement of the temperature, and this new measurement is saying that your temperature is 36 Celsius here. Okay, so the initial measurement at T, this is the initial measurement at T plus 1 is BT plus 1, and the apparatus you're using to take this measurement has an error of about 3 degrees. Okay, so what does that mean? It means that your true temperature could be anywhere between 36 plus or minus 30. So it could be 33 or 39. Okay, so this is the measurement error, and any apparatus measure anything has some kind of measurement error. So with your previous initial estimate, XT was 34 degrees. And at that time, you updated the estimation error or the estimate error to be EST, which is equal to 2 degrees. Okay, so your estimation is 34, and the estimate error is 2 degrees, which means that your estimation is in fact between 32 and 36 degrees. Okay. And here the Kalman gain first of all, let's try to create a formula. How can one update the Kalman gain? So the Kalman gain, or the Kalman coefficient, which is K here, is ES over ES plus EM at every T. Okay, so, and even write it as in terms of T if you wish. Okay, it's going to be updated. So in this case, at the beginning of T plus 1, since you've taken a new measurement, your EST is 2, which just comes from here, and divided by ES plus EM, which means it's 2 plus 3. So basically you get 2 over 5, which is 0.4. Okay? So if you use the updating scheme formulation, so your new estimate, which is XT plus 1, based on the measurement you've taken, okay, would be XT plus K times BT plus 1. In fact, this should be BT plus 1 minus XT, which should be equal here to how much? So your estimation was 34, this is XT, plus 0.4 times the difference, which is the difference between the measurement and the estimation, which is 2 degrees. 36 minus 34, which is 2. So basically, the new estimation is 34.8. Okay? So you see, the measurement you've taken has an impact, which is corrected by the Kalman coefficient minus the estimation. Okay? So the new measurement minus the estimation is corrected using the Kalman coefficient. So now you have a new estimation, which is 34.8. Okay? Now, this is not enough, because you need also, based on new estimation, to update this estimation or error you're carrying. As we said in the previous slide, maybe the most important input you're carrying with you, or the most important data with you, is how well is your model behaving or learning by itself from the new measurements and errors it makes. Okay? So you have to update here now the new estimation error. So at the beginning, like at the end of T plus 1, you get updated, which is equal to 1 minus T, so 1 minus the Kalman gain, or the Kalman coefficient, times the old estimation error. Okay? So of course, if the K is equal to 1, well, you reach your target, the estimation error is 0. Okay? So this happens when ES is equal to AS plus EM. So basically is the error measurement gets equal to 0. And this will never get equal to 0. So the best you could expect is that this estimation error could be very close, could be approaching 0. In fact, could be approaching 0. Okay, so this is the computation for just one measurement, which is BT plus 1. Do you have any question on this, guys? Okay, so let's see now we are enlarging the sample we take. So we are taking more measurements. So we now further develop and try to estimate the true temperature using a series of measures. And you see how the learning happens with this table. So in fact, this table maps the estimation updating scheme based on 7 measurements, okay? And 7, of course, Kalman filter iterations. So in our case here, this is at the beginning, before taking any new measurement. The estimation was 34, the measurement error was 2, the estimation error was 2, and we've also initialized the estimation error for the beginning of the next iteration to be exactly the same. To avoid any mistake. So now this is the t+1 we've considered in the previous slide, right? This happens. So now at t equals 1, we have this new measurement, which is 36 degrees, and the error measurement stays the same. Why? Because basically you're saying, like, to be consistent, I'm using the same apparatus to take all my measurements, okay? Which makes more sense. You cannot, change your apparatus during the experience. Definitely not, okay? Because this would have a funny impact on your results. So this is the result we found back in the previous slide, 34.8, and here we updated the K coefficient. Okay? So basically, we used the same error with which we entered the iteration, the estimation error 2, okay, and the measurement error to update our estimation, which is 34.8. And we finally end our iteration with a new estimation error, which is 1, as you've seen in the previous slide. All right, guys? Now you see that this, at the end of this iteration, the new estimating error would be used as the initial estimating error in the next iteration, 1.2. So with the new measurement now of 33 degrees and the same measurement error, I can update my estimation using the same formulation. So we said here that xt+1 at every iteration, xt+1, it's very easy to remember, is equal to xt, the old estimation, plus k times the new estimation, let's say it's bt+1 minus xt. Okay? Okay? And every time, of course, you need to use the updated Kalman gain, or Kalman coefficient. So with this new measurement of 33, you can easily do the math. So you can get 34.08 as a new estimation. Here, the updating gives exactly the same k, but the estimation error has changed now. It is 0.72. You take this new estimation error, you bring it to the next step, and I have a new measurement, which is much lower, which is 32, but a measurement error of 3. Okay? And I can use it to have a new estimate of my true temperature, 33.49, and I can update this way. I can get update my Kalman gain and update my estimation error. So what you can see after a couple of iterations here, just 7 iterations, in fact, is that what happens with the estimation error, it is decreasing. Okay, the estimation error is decreasing, which is a wonderful thing. The estimation error is decreasing, and you can see also the Kalman gain, or the impact of the estimation error, is also going towards 0, as you can see. So basically, what would happen after a number of iterations, so the estimation would almost be the same. Okay? And what you can, in fact, observe is that with a real temperature, which was 35 degrees, and then 35, in fact, had nothing to do with this. We have only based our estimation to our measurements and the measurement errors and our estimations and the updating scheme for the estimation and the Kalman gain. We were, in fact, in a couple of iterations, less than 1 degree from the true temperature we're trying to estimate. So what one can say is that the Kalman filter, in fact, brought us quite close to the exact value just in a couple of iterations. Let's have Aziz. Go ahead.
Doctor, what if the k values after each iteration it's going far from the zero, not to the zero?
There is something wrong with your either with the way you're computing it or the way the measurements are taken.
Okay.
Okay, because the way we are using it here, it's equal to ES divided by ES plus EM. So in all cases, it cannot be larger than 1. Get my point? And if you expect, yes, you get my point. So if you expect the ES to get closer to 0, the impact, since ES appears in the numerator here of K, the K can only go towards 0. If you suppose, of course, that you're using the same apparatus, so the AM basically is just a constant with respect to that.
Yeah.
Okay, get my point? So that's the example I wanted to share with you with the Kalman filter. Hopefully, maybe with more application, or maybe with the project, with the term project, you can choose, of course, to use a multi-dimensional and dimensional case of the Kalman filter. Okay? So hopefully this is clear. So now I'll move on to the last part in this section, which is 3.1. Just adding, in fact, kind of an extra note, which prepares us to the next section. So we introduce, in fact, in the textbook, this part appears just before the Kalman filter. We have chosen intentionally to delay it and put it at the end of the section because it prepares quite well the next section. So the derivative of A inverse. So now basically we're talking about differentiation, differentiating matrices. And this is a kind of calculus we mainly see in advanced math courses in engineering schools. So, so what is the main assumption here? Is that we need to think of A, in fact, as a time-related matrix. So A is a matrix which entries change with respect to the time. Okay. So basically, it would have what? It would have a set of derivatives. Okay. If you wanna, of course, even talk about higher order derivative. So its derivative with respect to t is dA over dt. And if t is changing, well, A inverse should be changing too. So the question here, how does A inverse change when A changes? So the desired change, Hassan. Yeah, so the entries here are in fact functions in terms of the time. Okay? And each entry here is a function of t. Okay? So how does A inverse change when A changes? Okay, so we'll see with the example in the next the next section. So that's the desired question. The desired change in A will, in fact, be very small, but of any rank. So let's first of all, just to understand the result we reach. So let's define B to be equal to A plus this change in delta. Remember in calculus 1, we've introduced delta x, which is small variation of x. So B is equal to A plus delta x. So basically, B is the new value or the new x. Okay. So B inverse minus A inverse is in fact the what is it? This is the variation in A inverse, in fact. And we can easily show that it's equal to B inverse times A minus B times A inverse. Okay? So delta A minus 1, or the variation in the A inverse, could be measured as B inverse times A minus B A inverse. So if you assume now that you have this set, okay, and divide by delta t, you are going to have delta A inverse over delta t, which is equal to, this part is B inverse. Okay, so this is B inverse, which is here between two brackets. Okay, and if you divide by delta t, Well, basically, you have delta A inverse over delta T equals minus A plus delta A inverse times delta A over delta T. Okay? Now, if you make delta T converge to 0, you obtain the differential form. So differential or dA inverse over dt is equal to, what happens here? The delta A goes to 0. So basically, the only thing you need to inverse now is A. So it's minus A inverse. And here what you have dA over dt times A inverse. Okay? So this is what would happen when you are talking about the expression of the derivative of the E inverse. Okay. For more, neat proofs or for more consistent proof on the results, you can go back to your to these sections in the book. Okay. I don't claim I can. I have the time to dive at this. So let's use these results. Okay? If you want to dig on it or to dig in it, please go back to the textbook. It's quite clear. Okay? So this last point will close section 3.1 and will help us also move on to section 3.2.